Hi, I'm Kunihiro Kato from Tokyo University of Technology. In this study, I'd like to talk about CAPath, the 3D printed interface to extend the capacitive touch input. With the widespread use of touch devices, such as smartphones, tablets, and touchpads, capacitive touch input has become one of the most common input methods. However, interaction with them is often criticized as lacking tactile feedback. To address this, researchers have developed physical objects that provide tactile feedback. These also have promising capability of enriching touch interactions, such as detecting tangibles and extending touch-sensitive parts from original touch devices. Some of the previous work intended to contribute end-user fabrication for the customized touch interfaces. In this work, we also contributed to the fabrication pipeline of touch interfaces. We propose CAPath, the 3D printed interface with multiple conductive points in a grid layout. It can be attached or placed on touch devices to realize various types of 2D inputs, include pointing and multi-touch gestures without active sensors or batteries. When the user slides a finger on the conductive parts of the interface, the contact areas are grounded sequentially, allowing touch operation in specific directions. Next, the fabrication process. Firstly, the user can design the touch areas by using the design support system we have developed. Then, by using exported 3D model, the user can 3D print the interface, and the user can interact with it. Here, we show a brief explanation of functionality of CAPath interface. Firstly, CAPath can transmit the finger touches or movements on the interface to the touch devices directly. In addition, it can transmit the contact area of the fingers. This interface has a grid layout on the center and several finger-sized contact points on the edge. It can be used in a drawing application to adjust the line width by swiping on the grid area, and to select the color of the pen by rotating the dial. This interface allows force-to-motion input, as similar to the conventional joystick attachment. In addition to this, our interface allows motion-to-motion input on the grid area. This interface can track a conductive disk so that the user can interact with both analog structure and smartphone game app simultaneously. CAPath interface can sense not only tapping or gestures, but also the contact area of finger. Next, CAPath interface can convert the finger movements in different directions. Furthermore, it can also change the CD ratio of the movements. This interface has two grid areas in which conductive paths are bent by 90 degrees. Users can use it as a game controller by inserting the smartphone vertically. This interface is a character stamp. It can convert one-finger swiping into Japanese characters and consists of 4 strokes. This interface converts all the gestures, such as tapping, scrolling, pinching, and rotation discharge, employed in common OSs. This is an example of converting the scale of touch movements. It allows changing the CD ratio between the finger movements and the actual touch input. Next, evaluation. Firstly, we evaluated the recognition accuracy of the one-finger touch operation with varied width and interval conditions. We confirmed that the accuracy decreased as the interval became wider. This was because for the wider interval, fewer conductive parts are grounded for finger touch, and sufficient current did not flow to the ground. Next, we then investigated the physical size scalability of the interface. Here, we evaluated the tapping and swiping operation with varied height conditions. The accuracy tended to decrease as height increased. We confirmed that height of up to 18 mm for one finger and 40 mm for two-finger operations can provide appropriate operability. Next, discussion. Firstly, the occlusion problem. We can consider that this problem can be reduced by using a structure for changing the CD ratio. In addition, we can implement a see-through interface by using a polyjet 3D printer. Next, although this work focused on the binary touch inputs, in addition to our proposed functionalities, by using the flow capacitive data, the CAPath interface is capable of enriching tangible interactions. For example, Omics Touch presented the application that detects the height of the 3D printed object with CAPath structure. This is conclusion. The 3D models and G-codes to fabricate our interfaces are available on my personal webpage. Thank you for listening.